Hello everyone, welcome to my YouTube channel. So in this lecture, I will teach about the infrared spectroscopy in the organic chemistry. So before that, I will give a brief introduction about the infrared spectroscopy. So infrared spectroscopy, when electromagnetic radiation from ultraviolet to microwave region is passed through a sample of an organometallic compound, some of the frequency are absorbed while other frequency are transmitted to the sample without being absorbed. So these depend on the nature of the substance. Now the radiation is a source of energy. So energy of the radiation del E is equal to hv. So thus by the absorption of the radiation of energy del E is gained by the molecule. So as a result, there is a increase in vibrational and rotational energy of the molecule. Even an electron may jump from lower energy level to higher energy one. So almost any compound having the covalent bond, whether organic or inorganic, will be found to absorb various frequency of electromagnetic radiation in infrared region of the spectra. The infrared region of the electromagnetic radiation lies at the wavelength longer than the associated visible light, which include the wavelength from approximately 4 nanometer to 800 nanometer. But liest is the wavelength shorter than the associated with the microwave, which have the wavelength longer than the 1 mm. Now a plot of transmitters against the wave number of an organic compound, the intensity of the given compound. So this is a higher spectroscopy or of an organic compound. So here y-axis is the transmission and x-axis is the wave number. So infrared spectroscopy is basically the vibrational spectroscopy. It's highly characterized in the compound structure. Now in the different bonds have the different vibrational frequency, and thus we can detect the presence of this bond in an organic molecule by identifying this characteristic frequency as an absorption band in the structural spectra. Thus, the infrared spectroscopy targets leads to a detection of the functionalities of the organic compound. So that means in the infrared spectroscopy, a light source is transmitted to a compound. So the functional group present in this compound will absorb the frequency of a given wavelength. So then there is a electron transition from the lower energy state to higher energy state of the molecule, and then we should detect the absorption spectrum. Then we detect the absorption in the infrared spectroscopy. So different type of bond has a different type of vibrational. So infrared frequency is basically a vibrational frequency. So different type of bond have different vibrational frequency. So that will be absorb different wavelength. So this is the infrared spectroscopy. The characteristic for the different bond. So by the infrared spectroscopy, we can detect the functionality present in this organic molecule. So electromagnetic radiation is a wave phenomenon. So characterized by the wavelength or frequency. So wavelength defined as the distance between the adjacent peaks and may be designed as meter, centimeter, or nanometer. So and frequency is the number of wave cycles that travel past a fixed point per unit of time, which are given per cycles per second. So this is the wave. So there are two terms. One is a wavelength, one is a frequency. So wavelength is the distance between the adjacent peaks. So here these two peaks. So the distance between these two peaks is called the wavelength, and frequency is the number of cycles that travel past fixed point per unit of time. So a unit of the wavelength is in the meter, centimeter, or nanometer, which is a length, the unit of the length, and the frequency is the cycle per second. So that is or hertz. So wavelength of a electromagnetic radiation is related to the frequency. Mu is the radiation, so mu delta is equal to c. So here mu is equal to frequency, delta is equal to wavelength, and c is equal to velocity of the light. So because of the great difference in the wavelength in various regions, it is convenient to use the same unit through the out of specific particular position in the spectra. In the infrared region, the wavelength are expressed in the micrometers and the reciprocal wavelength is centimeter. 1 by delta is 1 by lambda comes as a wave number. The unit of the wave number is a mu bar is a 1 by lambda. So for the infrared region wavelength 0.80 micrometer to 0.25 micrometer, and wave number is 400 to centimeter inverse to 12,000 inverse. Organic molecules of the infrared spectroscopy are almost entirely concentrated in range of 650 to 400 centimeter inverse. So the unit of wave number is equal to the unit 1 by unit of the lambda, that is centimeter. So the unit of the wave number is the centimeter inverse. And so for the organic molecule in the infrared spectroscopy, the entire range is 400 to 600 to 4,000 centimeter inverse. This is the mid infrared spectroscopy, and the region of the frequency lower than the 500 centimeter is called the far infrared, and that of the frequency higher than the 400 centimeter is called the near infrared. So now I will discuss the molecular vibration. So what happens if a molecule absorbs the IR radiation? So at ordinary temperature, organic molecules are in a constant state of vibration, each of bond having its characteristic stretching and bending frequency and being capable of absorbing light that of frequency. By the absorption of IR radiation, there is a change in molecular vibration level. So here it is a two state. By absorbing the higher stretching frequency, the molecule can go in the higher region or down to the lower region. So thus, during the change in the vibrational change in the energy level, we do expect a sharp light, but instead of sharp light, we got broad band as obvious from the sample of the infrared spectra of proton. So one of the reason is the band is broader than the sharp in the infrared spectra. The rotational coupling. So each vibration energy level are associated with the number of rotational energy levels, which may lead to considerable amount of unresolved fine structure. There are the two types of fundamental vibration: stretching and bending. So normal by theoretically the spectra of a vibration stretching frequency should be sharp, but here the spectra is a broad. So the spectra is broad due to the each vibrational level is constituted with a rotational energy level. So which may lead the considerable amount of unresolved fine structure. So that's why the spectra in the vibrational stretching frequency is the sharp peak. So in the rotational frequency, there are molecules. So vibrational, there are two types of vibrational. One is a stretching, one is a bending. So although rotational frequencies of whole molecule are not infrared active, they often couple with the stretching and bending vibration in the molecule to keep the additional fine of this absorption of further complicated spectra. So the vibration of the two atoms joined together by a chemical bond or can be linked with the vibration of two balls. When to it, that the stretching energy is greater than the bending energy. The stretching absorption of the bond appear higher frequency in the infrared spectrum than the bending energy. So there are two types of vibration. One is stretching and bending. So the stretch requires more energy than the bend because the stretch energy is greater of bending. The stretching appears, so that's why the stretching absorption will form with higher frequency range than the bending. So the stretching mu bar for stretching is greater than the bending. So now the vibration, stretching or bending of a bond occur at a certain quantized frequency. When the IR of the same frequency is incident on the molecule, thus only the energy will be absorbed and amplitude of the vibration is increased. So now we will discuss about the mode of vibration. So molecule with a large assemblage of atoms possess huge number of vibration frequency. For non-linear molecules with the n atoms, the number of vibrational modes of Cn-6. Thus for the triatomic non-linear molecule, we have the 3 modes. So here For the nonlinear molecule, like water molecule, here it was 3 triatomic nonlinear molecule, here 3n minus 6. That means 3 minus 3 minus 6 equal to 3. So that means here total 3 vibrational stretching frequency. So one is the symmetric stretching, and is the anti-symmetric stretching, and one is the cis curving or the bending mode. So here the stretching symmetric stretching means here this is a central atom. Here the same direction the two bond will stretch, that is symmetric stretching. In the anti-symmetric stretching, the direction of stretching of the two bond will be the different, and in the cis curving is the bending mode where in plane these two molecule will come closer. And for linear molecules, the 3n.5 of vibration stretching for n of the number atom, that like the CO2, there are total 4 types of vibration frequency. 3n minus 5 means 3 into 3 minus 5. So here total 4, like the CO2. So here CO2 has a 4 bending mode. One is the symmetric stretching, one is the anti-symmetric stretching, one is the bending in the in plane, and in the bending out of plane. So symmetric stretching, that means the stretching of the two bond in the same direction, or anti-symmetric stretching of the two bond opposite direction, and it is an in plane bending, and it is an outbound bending. So here the bending vibration are equivalent called the double digit. Now for the AX2 type molecule of grouping, we have the following modes of vibration. So AX2 type vibration is AX2 type, they are total symmetric stretching and the anti-symmetric stretching, and the bending mode is the cis curving and rocking, in plane deformation or out of deformation, twisting or wagging. So each of the different vibration modes may give rise to different absorption band. So that for the CH2 group rise to the two CH stretching band, sigma symmetrical and sigma antisymmetrical. However, all the vibration not give rise to absorption, since some of may have the same frequency, that are the degenerate, and their absorption band will overlap in addition some vibration. So in any group of 3 or more atoms, at least 2 of which are identical, they are the two modes of stretching, symmetric and asymmetric. For example, like methyl, the symmetric stretching means all the stretching will come. This is symmetric methyl group, it comes at 2870 centimeter inverse, asymmetric stretching, and for anhydride, the symmetric, this is the mode of symmetric stretching, this is the mode of asymmetric stretching, which comes at 800 1800 centimeter inverse, and for amino, the two is in the same symmetric stretching, and here for the asymmetric stretching which come as a 3400, and nitro the symmetric stretching and the asymmetric stretching. So here the asymmetric stretching frequency will be give higher stretching frequency than the symmetric one. The vibration we have discussed, it lead to the fundamental adjustment. They rise from the excitation from the ground state to the lowest energy excitation state. So usually spectrum is complicated because of the presence of weak overtone combination and different band. So overtone means the result from the excitation from the ground state to higher energy state, which falls in the integral multiples of the frequency of the fundamental. For example, the weak overtone bands is come at the 2 times of the mu bar, theta mu bar, and any kind of the physical vibration generate overtone. So any absorption in the infrared at 500 centimeter inverse may will have the upcoming peak of the lowering frequency intensity at 1000 centimeter. That is a overtone band. So when two vibrational frequency is a molecule coupled to rise a vibration of new frequency within the molecule, such vibration is infrared active. This is called the combination band. So combination band when two means when the two vibrational frequency is coupled together and give a active vibrational frequency range. So combination band is open the two interacting bands. So mu bar combination is equal to 1 plus mu bar 2. So not all possible combination occur. That the rule that govern which combination is allowed are beyond the scope of our discussion here. So difference band are the similar to combination. The observed frequency of this difference band is the mu difference, mu bar difference equal to mu bar 1 minus mu bar 2. So here difference band means between the difference between the staging frequency of the two vibrational staging frequency. So when a fundamental vibration coupled with the overtone or combination band, the coupled vibration is called the Fermi resonance. So again, only one certain combination are allowed. Fermi resonance is often observed in the carbonic compound. So next we discuss the which fundamental vibration are the IR active. So a molecule have many types of vibrational staging frequency, but all the vibrational staging frequency is not IR active. So there must be some rule for the selectivity of which IR bands is the IR active. So only those fundamental bands which are associated with a rhythmical change in the dipole moment are able to absorb in the IR radiation. So that means the fundamental vibration which can change the net change, which can create a net change in the dipole moment in a molecule, that way is the IR active. So this change is the dipole moment is altering the electronic field. So infrared light is absorbed when the oscillating dipole moment interacts with the oscillating electronic vector of the infrared beam. Thus, a simple selection rule of the absorption in the infrared region is the change in the dipole moment due to the molecular vibration. So symmetric bond such as H2 or Cl2 do not observe in the infrared region. So the symmetric molecule like H2 or Cl2, their symmetric staging frequency is not infrared active because they are not changing a dipole moment in the molecule. So a bond must present an electrical dipole that is changing the same frequency at incoming radiation from energy to be transferred. Thus, a symmetric bond that is identical or near identical group on each will not absorb in the infrared region. So these are the referred as symmetric or pseudo-symmetric molecules respectively. So this is the symmetric molecules, the infrared frequency is not active. Obviously, the symmetric vibration of CO2 is IR inactive. In their case for C double bond or ethylene or C triple bond of acetylene. So the important consequence of this selection rule is that the molecule with the center of symmetry, those vibration symmetrical about the center of symmetry are inactive. In the infrared, those vibration are under centrosymmetry are usually active in the infrared spectroscopy. Thus, and the IR spectra is very informative for the organic chemists as a fundamental group are not centrosymmetry. So now I will discuss about the uses of the infrared spectra. Since every type of bonds with a different natural frequency of vibration, since two types of same bonds in a two different compound in slightly different environment are not two molecules of the different structure have exactly the same infrared absorption or infrared spectra. So although some of the frequency absorbed in the two cases might be the same, in no cases two different molecules will their infrared spectra be identical. Thus, the infrared spectra can be used for molecules such as fingerprint, can be used for humans. By comparing the infrared spectra of these two subjects can be judged whether they are identical or not. Since the region of current system is completely formed, this region is often called the fingerprint region in the infrared spectrum. So that means the different if one in a one molecule there are two types of functional group, but their chemical environment is not same. So then their vibration staging frequency is not the same. So that's why we can identify the between these two functional groups. So it is the fingerprint region. The IR spectra is the fingerprint for detect the can define chemical environment of this functional group. And second and more important use of the infrastructure is the determine the structure information about the molecule. So absorption of each type of bond A, CH, OH, CX are regularly found in a certain small portion of hybrid. A small region of absorption can be identified each type. So they illustrate the schematic how this separate our. So that means if such is in a molecule there is some OH or NH bond, so the vibrational stretching frequency of the OH or NH bond is not the same. So by the infrared spectroscopy, we can detect whether this is a OH bond or whether it is a NH bond. So so that means by the infrared spectroscopy, we can detect the different functional group, different bond in the infrared organic molecule by the infrared IR spectroscopy. So now we use the calculation of the vibrational frequency. So if a diamagnetic molecule can be considered as a two vibrating mass connected by a spring, the bond distance continually changes, but the equilibrium average bond distance can be defined. Whenever the spring is stretched or compressed beyond the equilibrium distance, the potential of the system increases as per any harmonic oscillator. When a bond vibrates, its energy of vibration is continuously or periodically changing from kinetic or potential energy back again. We can calculate the vibrational frequency of a bond by using Hooke's law, which correlates the frequency. So this is the Hooke's law, where mu is equal to 1 by 2 pi root over k by mu bar. So according to Hooke's law, mu is equal to 1 by 2 pi by k by mu. So here mu is the frequency of vibration frequency absorption frequency. So k is the force constant which depends on the strength of the bond, and mu is the reduced mass for like two molecules. The reduced mass is the m1 into m2 by m1 plus m2. So this is the derivation of the Hooke's law. So suppose we can calculate the approximately frequency of CH stretching frequency. So suppose let's see the bond constant k is equal to force constant of a CH bond is 5 minus 10⁵ grams per second, and the reduced mass and the mass of the carbon is 12.1 grams and mA. So right here the stretching frequency of nu is equal to 9.242 × 10⁵ second inverse. So consequently, the nu bar CH, which is 1, is equal to mu by C. So that is a 300 800 inverse. So within the limit of so CH stretching frequency is in the region of 3880 centimeter inverse. So extract the structural information of the infrared spectra. You must familiar with the frequency and with the various functions. So we may consult infrared tables to provide some information. So different type of bond as the different infrared spectroscopy. So here the so in the CH bond length for the alkane, the neovast stretching frequency 3200. For CH3 bending or 400. For alkynes, the CH frequency 300 to 3100 to 3000 inverse aromatic region. For the alkane stretching C3 double bond alkene in 168 to 1600. For the aromatic 1600 to 1275. For the alkyne, for nitriles, and the CO stretching frequency for aldehyde, ketones, carboxylic acid, ester, amide, anhydride, acid, acid chloride, anhydride, and C double bond, amine or oxime. And so for the alcohol, CO stretching frequency. For OH, alcohol, phenols, 3 stretching frequency, 8 stretching frequency. For NH proton, the stretching and bending. For CN1 amines, for C double bond amines and oxime, C triple bond nitrile. This is the stretching frequency of common organic molecules. So we are now will discuss about the effect of the force constant and the mass. So let us now consider how the bond strength and the mass of the bonded atoms on the infrared absorption frequency. For sake of simplicity, we restrict the discussion of the simple heteronychal diatom molecule, and the steady stretching frequency we have mu bar is equal to 1 by 2 pi c k by mu. So from the above equation, the mu bar is dependent on the two things. One is the bond force constant bond, and one is the reduced mass. So that means the stronger the bond has, the stronger this is mu bar stretching frequency, and the greater the reduced mass, the lower is the stretching frequency. So that means for the above equation, there is one is the stronger bond have the larger force constant and vibrated at higher frequency, and then the weaker bonds. The second is the bond between atoms of higher masses vibrated lower frequency than the bond between lighter atoms. So let us consider these three cases, the CH, NH, and OH. So here we expect the similar, the reduced mass is exactly like 1. We expect a similar stretching frequency for 1, but now we have the OH bond at higher stretching frequency compared to the NH bond compared to the CH bond. So a higher electronegativity or O atom makes the O and H bond stronger. So that's why the CH stretching frequency are 3000. So here the force constant plays a role. So for the OH bond, the force constant is the higher. So that's why the OH bond is stretching frequency is the higher than the CH or NH bond. So let's consider the case of reduced bond. For the CC bond, NC bond, OC bond. For the CC bond, reduced bonds are 6, the NC bond reduced bond is 6.46, and the OC bond reduced bond is 6.85. So OC bonds have the higher reduced bond. So since the electronegativity of carbon and hydrogen commonly is the same, the force constant is CH bond in constant similar to CC bond. Thus on the average, so mu bar Cc is equal to 1 to 4.7 bar. So now on the descending, the force constant of the ZC extend upon the increase the nitrogen or oxygen at higher. At the same time, the reduced mass increases 2 factor are in the opposition. The absorption frequency of Cc and when the region of 200 inverse. So as the atom bonded to the carbon increase in mass, the reduced mass increases and the frequency of the hydrogen decreases. So here, so CH, CC, CO, CL, CRBR, here the reduced mass of the two atoms is increases. So that's why the increase the mu, the stretching frequency is decreases. So again in comparison between OH and OD bond, so mu bar of the OD bonds is low. The mu bar of the OD bond is 3600 and then OH bond OD bond is 634. So here the OD bond has a higher reduced mass, and that's why the stretching frequency is low. So in general, triple bond are stronger than the double bond or single bond between the same two atoms. The two higher frequency. So here the CC bond has the stretching frequency near 1200, C double bond C 1650, and C triple bond C 150. So here the force constant between the two bonds is a crucial as the triple bond has the more force constant than the double bond and single bond. So force constant, so that's why the stretching frequency of the triple bond is higher than the double bond and single bond. The force constant of a double bond is nearly double that of the single bond, and the force constant of triple bond is nearly thrice the single bond. Thus, the wave number of the carbon-carbon double bond can be calculated by multiplying 1200 seminars with the square root of 2, and that for the carbon-carbon triple bond can be calculated by multiplying the square root of 3, actually in the limit of approximation. So hybridization affects the force constant. So bonds are stronger in the order sp, sp2, sp3. That is with the increase of the s character, bond length increases. Thus, the observed frequency of CH hydrogen increases. So that's mean when there is a more s character in the orbital, that bond is more strong than the stretching. So that will give the more stretching frequency in the infrared spectroscopy. Now I will discuss about the ring size effect. So ring size effect with the external double bond. So external exo double bond give the increasing active frequency with the decreasing ring size. So here the ring size will increase, but the stretching frequency is decreased. So this is the reason the smaller ring size. If we are more use of more peak character to make the CC bond from the requested small angle. These remove the P character from the sigma bond of the double bond, give it more S character. Thus, the changing and steppering the bond, the force constant K is increased, the absorption frequency is increased. So alene is included in the series. This is the extreme example of exo double bond absorption. However, the inventor that the alene central carbon is the square with the guitar is character and for the sp2 hydrogen metal. So here is a reason is that here when the ring size is decreased, so sp orbital has 180 angle, sp2 has 120 angle, sp3 190. So that means more the p character, the more will be the bond angle will be decreased. So here upon the decrease in the rings, when the small ring has the more p character in the inside of the orbital, that means the more p orbital is used to form this cc bond. So that's why the increase in the s character and the external double bond, so that will increase the overall force constant with this molecule. That's why the overall force constant of the molecule is increased. That's why it is absorbed in the more infrared spectroscopy. So that's why the external bond with a small ring size will have more stretching frequency. So next we will discuss about the ring size effect with internal double bond. So the absorption frequency of the internal double bond in the cyclic compound is very sensitive to the ring size. So the absorption frequency decrease as the internal angle decrease until it reaches minimum at 90 degree at cyclopropane. The frequency increase again for cyclopropane when the angle drops to 60 degree. So here is the when here up to this there is a decrease in the stretching frequency with the decrease in the ring size, but for the cyclopropene, the ring upon decrease of the ring size, but here the increase in the stretching frequency. So the initially unexpected increase in the frequency occur because the CC vibration in the cyclopropane is strongly coupled with the attached CC double bond vibration. When the attached CC bond are perpendicular the CC double bond C axis, and in the cyclobutene, their rotational mode is orthogonal so that the of the CC double bond does not couple. When the angle is greater than 90, the C single bond stretching vibration can be resolved into two components. One of the coincident with the direction of CC state. So that means when the attached CC bond is perpendicular to the CC double bond axis, like the cyclobutene, the vibrational mode is orthogonal to the CC double bond. So they do not couple. But when the angle is greater than 90, the CC single bond is stretching vibration resolved into two components. So here for the cyclobutene case is 90 degree, this is not coupled. But here the CC double bond is a two components. So here it so components A and B of the CC stretching vector are shown. Since the component A in the line of the CC stretching vector and the C and CC bonds are coupled, leading to the higher stretching frequency. A similar pattern exists for cyclopropane, which has the angle less than the 90 degree. So here the CC bond has a two vector position, one direction of A, one direction of B. So this A is direction of the this C double bond C. So that will couple with the C double bond C. So that's why the upon increase the ring size, the CC double bond stretching frequency increases, and also for the cyclopropane case, these things happen. So that's why it is increased. So this fact is also helps to explain the effect of the alkyl substitute on double bond. So significant increase the frequency of absorption of double bond contained in a ring are observed when two or alkyl groups are attached direct to the double bond. As there, the increase in frequency occur because of CC hydrogen strongly coupled to the attached CC single bond hydrogen. So the increase is the most dramatic for the small ring cyclopropane. For example, the base value of cyclopropane increase about when the one alkyl group attached to double bond, two alkyl group attached. So here, when the alkyl group is substituted to the small internal double bond, so upon the substitution of the internal double bond, the stretching frequency will increase due to the more resolved coupled with the same single bond to the double bond. Same case happened to the cyclobutene or cyclopentene. So here is the increase of the stretching frequency. Now I will discuss about the electronic effect in the stretching frequency. So we found that the vibrational frequency of a bond depends on its bond strength. Now the increase in the polarity of the bond strength increases. So electronic factors that affect the bond strength of the different functional groups, the carbonyl groups is present in aldehyde ketones, amide esters, amide chlorides, and anhydrides group absorb strongly in the range of the 1850 to 1650 centimeter because each larger change in the dipole moment. So the stretching frequency is sensitive to the attached atom. The stretching frequency of ketone, which is approximately middle range, usually considered the reference spread for comparison of the values. So that means the more the polarity of the bond, that will increase the stretching constant, that will increase the stretching frequency. So this is the here the ketone, carboxyl acid, amides, aldehyde, esters, anhydride, acid chloride. The stretching frequency are summarized in this table. So ketone has the middle range 1715. Upon this side, the stretching frequency increases, and this side stretching frequency decreases. So amides and carboxylic acid that is has the lower stretching frequency that the aldehydes and ketones. So we'll discuss this that is this reason in the next lecture, how the substitution effect or the electronic effect will affect the CO stretching frequency. So thank you.